on.
All right, so let's get going here. Greetings, my name is Devendra Das Sarma. I work for Intel, and I'm going to talk about PCI Express architecture and high performance computing, especially as we move towards the higher speeds and feeds with PCI Express 6.0. So this slide shows about the journey of PCI Express. It has been a 2-decade journey. We have been doubling the data rate every generation with full backward compatibility for the last 2 decades. And this happens roughly every 3 years. And the timelines are given here. So if you look at this, you will see that these are the different generations of the data rate. These are the raw data rate speed, the encoding that goes with that, how much of aggregate bandwidth you would get per direction. And you can see that once we are at 6.0, we are at about a terabit per second per direction. And the year in which it is supposed to come out is next year. So PCI Express is the ubiquitous I/O across the entire compute continuum, right? Everything from your handheld PC, server, cloud, enterprise, anything and everything has got PCI Express. And we have been successful because we have done one stack, same silicon that works across all the segments, across all the widths, whether it is a by 1, by 2, by 4, by 8, by 16. But we support different form factors. So it is the same silicon, same stack, same software but works across a wide range of computing needs. And to the extent that you can put a by 16 Gen 5 device and it will interoperate with a by 1 Gen 1 device, right? That's the promise of backward compatibility. And we are on this trend. We will continue to double the data rate, and we are on track for the 6th generation. So pretty excited about that. So what are the drivers actually? Why do we need to drive these data rates, right, at the rate at which we are driving? So if we look into the segments, it's high performance computing, cloud, automotive, enterprise, client, storage. All of them, right? All of them have tremendous need for speeds and feeds, right? Our compute capability is growing. The demand for memory bandwidth and memory capacity is growing, and the demand for the IO bandwidth is growing. On the device side, if you look into networking, is expecting to go to 800 gig in early 2020s. Accelerators have an insatiable demand for bandwidth. FPGA, ASICs, memory, you can throw as much of bandwidth as you want, right? And there is just tremendous amount of demand there. On top of that, what we are seeing is we are seeing alternate protocols, for example, like Compute Express Link, which has coherency and memory semantics. Those are running on PCI Express physicals. So they also have a lot of demand for the bandwidth. So effectively, we are in this you know in this world where more capability means you have to drive more speeds and feeds into the system, and that's causing new usage models. So we are in this virtuous cycle of computing where we need to keep up with that pace. Now, however, and the other thing that you will notice is that the number of lanes of PCI Express that are coming out of a socket has also increased. So not only is the per pin bandwidth going up, the number of lanes that are coming out of a CPU socket has also been growing, which basically means that people not only need more bandwidth per pin, but also they need more aggregate bandwidth. So with all of these, there are a few things to keep in mind. With 128 lanes, you need to be extremely careful about cost. You need to be, of course, careful about performance because it is a load store IO interconnect. You need to be very careful about power, right? So these are the things that we need to keep in mind. We need to make sure that we are not changing those things. We are, of course, delivering better performance, but we can't be increasing power tremendously. We can't be, increasing cost, because then you're not going to be a ubiquitous IO. You're going to become a niche IO, and that's not where PCI Express is. So we need to also make sure that any of these speeds and feeds that we do can scale to hundreds of lanes in a platform. So, with all of these, the way we do things is we basically, before we embark on a technology development, we lay down clear metrics. And so these are the metrics for 6.0. We had similar set of table for 5.0. Data rate, of course, 64 giga transfers per second. We double the data rate every generation. So Gen 5 was 32, Gen 4 was 16. So Gen 6 will be 64 giga transfers per second. At these data rate, for cost and all of those reasons, it has to be PAM4 for the type of reach that we want. So 64 gig PAM4. Now the problem with the challenge rather with PAM4 is that you need to do forward error correction. So what we said is the latency adder, because of forward error correction plus anything else, needs to be less than 10 nanosecond for transmit plus receive over what is there in 32 gig. And we just cannot afford the 100 plus nanosecond FEC latency as networking does with PAM4. It just does not work for a load store IO. Let alone PCIe, it definitely is not going to work for other coherency and memory semantics. From a bandwidth inefficiency point of view, we want less than 2% adder over 5.0. Reliability is calculated in FIT, which is failure in time. So we want it to be very close to 0, significantly less than 1. Channel reach similar as PCIe Gen 5. Power efficiency better than 5.0. And low power, we added a new low power state called L0P. And plug and play, we want it to be fully backward compatible and all of that. And then in general, we want it to be high volume manufacturing ready, cost effective, and be able to scale. So the question is, how are we doing this? So PAM4 means higher error rate, and those error rates will translate into burst errors because we have decision feedback equalizer. So basically we did a study here, and that study says that there is a trade-off to be made between what we call the raw first burst error rate, FBER. A lot of people call it just raw BER, but FBER is the way to think about it. If you change that here, and then you look into the different type of FEC characteristics, what we found is if we choose the 10 to the power minus 6 as the raw FBER rate, we can really choose a very lightweight FEC. The other advantage a PCI Express has is that it has fundamentally a link level replay mechanism built in. So what we said is we go with -6 as the raw FBER. We choose a very lightweight FEC, so that just puts us right to an acceptable retry probability. So, we basically want our probability of retry on a flit to be 10 to the power minus 5 to 10 to the power minus 6. So once that is there, we keep the latency really low. We keep the replay latency really low also on top of that. So when we do that, we have a very, very robust solution. And from a fit point of view, we basically went ahead and increased the CRC to 64-bit CRC. So the combination of all of these gives us a really compelling solution. And this one also shows the bandwidth loss, and you can see that in most of the cases, what happens is that our retry probability is fairly low. That means that we don't get as much of replay, and it works out really well for us. This picture here shows roughly what the layout is of FLET. So you can see that basically the FEC that we have chosen is a 3-way interleaved. So each color is one FEC group. And you will see that there are ECC, there are 6 bytes of ECC here at the end of it. So it's 2 bytes of ECC per group. So we just correct one symbol error. And you can see that burst error is corrected because any burst is going to be contained within 3 bytes effectively, right? So that's how you are going to correct a burst error. And the first 236 bytes here are for what is known as transaction layer packets. So this is the regular TLP. Then you got 6 bytes of what we call data link payload. So these are the things like your ACK-NAC. So we are providing a guaranteed slot for doing ACK-NAC. That way you are trying to keep the, loop latency between a transmitter and a receiver really, really low. So you send a packet, you should get an ACK back in 100 to 200 nanoseconds. And because there is a guaranteed slot there, and you got 8 bytes of CRC. So basically it's fairly robust. Our fit is at a very close to 10 to the power minus 9. So which means 10 to the power minus 9 failures every 10 to the power 9 hours. So which is pretty good. And then you got the ECC. So with all of these, our bandwidth efficiency, if you look into it, anytime we are significantly less than as not significantly less than 2, we are doing pretty good, which means that I'm getting 2x more bandwidth than 32 gig at 64 gig. And you can see that by the time my payload hits somewhere around, this is D word, by the way, which means that 256 bytes are 512 bytes, 4096 bytes. So by 4096 bytes, we start degrading compared to Gen 5. But other than that, we do pretty well. In fact, we get a lot of bandwidth efficiency advantage because we have been able to remove a bunch of inefficiencies from that used to exist from before. And then these are the flit accumulation latency: 2 nanoseconds, 4 nanoseconds, 8 nanoseconds, 16, and 32 for a by one. The FEC overhead in terms of the latency by itself is it's very easily doable in 2. We think it's we have actually proof that it is less than a nanosecond, both FEC plus CRC. So the overhead in terms of latency is fairly low. Probability of retry, as we saw in the prior slide, is also very acceptable. And fit is 10 to the power minus 9, which is, so we got a very compelling solution. Now, maturity wise, PCIe 6.0 specification, it's at Rev 0.7 level. As we talked about, it's new signaling with PAM4. We did the trade-off around error. We made sure that we are taking into account correlation of error within a lane as well as across lanes. The channels, the performance that you're going to get, the area that you're going to take to implement in the logic, circuit complexity, with all of that, it's looking pretty good in terms of doubling the bandwidth. The metrics that we talked about in the very earlier slides, they are significantly challenging, but we have been able to accomplish all of that, especially around the latency goals and the bandwidth inefficiency goals. And in general, we are on track to exceed or meet the requirements and doing all the analysis. So this high bandwidth that we have with the low latency and low power, by the way, right? Both are important because with hundreds of lanes, with that much of bandwidth going in and out of the socket, power, latency, all of them are critical. It's designed basically to benefit applications such as those that you're pursuing for the OCP, high performance computing, NIC, accelerator, storage. You know, everybody needs PCI Express. So really glad that we are able to continue on this journey and provide high performance, high reliability, high bandwidth solutions at a low cost. So if there are any questions, we'll take those.
Devender, I don't see any questions in the chat right now. Let me see. Nothing's coming through on the chat or even on the Etherpad. So I guess maybe you answered all their questions.
Archana, if you have time, I have a question for Devendra.
Sure, go for it. We have about a minute.
So especially, the audience here is OCP audience. We're all trying to build wonderful products around these technologies. The challenges and the type of problems that we're trying to solve with PCIe Gen 6. Devendra, do you anticipate work that we need to do in defining new form factors, new connectors, new PCB material? Give us some guidance in that regard as well, please.
Sure. So actually, that's a very good question. In general, the materials, they improve over time. So as you improve over time, what it does is it increases the reach, right? So right now we are targeting, roughly about 12 inches on the motherboard with the type of material that we expect. Form factors always, with these speeds and feeds, let's say, can we do interesting things with cables, for example? That will be very exciting to go and explore, right? In terms of disaggregation and all of those good stuff. The existing form factors, we of course will make sure that they are going to scale, like the traditional chem form factor. There are some enhancements that needs to be done so that you can continue to work in a fully backward compatible manner. But basically, the higher bandwidth and speeds and feeds allows us to explore new usage models like disaggregation and those kind of things in a cost-effective manner. So yes.
The vendor, I don't know if this is directed at you, but there's a question on the Etherpad that says, does PCI Express Gen 6 address the number of bus IDs assigned in topologies with multiple switches and switch hops?
Those two are orthogonal, but yes, PCI Express, we have defined the notion of segments in order to allow for more number of bus numbers. So the answer is yes, those have been there, but that's orthogonal to the speed. You could do that for the earlier speeds too. Yeah.
Okay. Thank you so much for your time. We really, really appreciate it.
Thank you.
I've got the TE team on standby here. Chris, I think you will be presenting. So Devender, thank you again.
Sure,
If we do get any questions, just pay mind to the Etherpad and we'll be posting them in there on the FN Virtual app.
Sure.
So we've got Chris and David from TE.